May 9, 1943, 11:27 a.m. Wright Field, Dayton, Ohio. Captain Howard Miller throttled back the Allison V-1710 engine of his P-38 Lightning to cruise power, leveled off at 22,000 feet, and checked his fuel gauges with growing disbelief. According to the gauges, after 2 hours and 14 minutes of flight, he should have consumed approximately 460 gallons of fuel from his total capacity of 410 gallons in main tanks plus 300 gallons in drop tanks. The mathematics were impossible. He should have been flying on fumes, preparing for emergency landing. Instead, his gauges showed 180 gallons remaining, enough for another hour of flight. Either his instruments had failed catastrophically, or something was fundamentally wrong with every fuel consumption calculation the Army Air Forces had ever made for the P-38. Miller keyed his radio to report the impossible data to Wright Field Control Tower. Tower Lightning 37 experiencing instrument anomaly. Fuel gauges reading 180 gallons remaining after 2 hours 14 minutes flight. Request permission to continue flight to validate readings or declare emergency if instruments have failed. The response came after a long pause. Lightning 37, your instruments are functioning correctly. Continue flight as planned. We will explain when you land. What Captain Miller didn't know, what Wright Field engineers were still struggling to believe themselves, was that a civilian aeronautical engineer named Charles Taylor had just proven that everything the Army Air Forces understood about aircraft fuel efficiency was wrong. Taylor had demonstrated that a simple modification to engine cowling airflow, accomplished with sheet metal baffles costing $6 and requiring 4 hours to install, could reduce fuel consumption by 33% and extend range by over 50%. His discovery violated every principle of aeronautical engineering that designers at Lockheed and the National Advisory Committee for Aeronautics had established. It contradicted decades of wind tunnel testing and theoretical analysis. It made no sense according to fluid dynamics calculations that government engineers had verified repeatedly. But it worked. And within 6 months, Taylor's crazy airflow trick would transform every American fighter aircraft from short-range interceptor, barely capable of escorting bombers to Germany's borders, into long-range escort, capable of protecting bombers all the way to Berlin and back. It would change the strategic bombing campaign, save thousands of bomber crew lives, and help win the air war over Europe. This is the story of how one engineer's refusal to accept established aeronautical wisdom created capabilities that experts said were impossible, how cowling baffles changed warfare, and how sometimes the craziest ideas are crazy only because everyone else stopped questioning assumptions. The crisis that would bring Charles Taylor to Wright Field began in summer 1942 when the 8th Air Force commenced strategic bombing operations against occupied Europe. The theory behind daylight precision bombing required fighter escort to protect bomber formations from German interceptors, but escort required fighters with range-matching bombers, which American fighters simply didn't possess. The Republic P-47 Thunderbolt, America's primary escort fighter in early operations, had combat radius of approximately 475 miles with internal fuel and drop tanks. The Lockheed P-38 Lightning offered slightly better range at approximately 520 miles, but meaningful strategic targets in Germany were 600 to 800 miles from English bases, well beyond escort range. The consequences were catastrophic. Unescorted bomber formations suffered losses approaching 30% on deep penetration raids. The October 14, 1943 raid on Schweinfurt lost 60 bombers out of 291 dispatched, a 20.6% loss rate that was unsustainable. At such rates, bomber crews had statistical life expectancy of approximately 12 missions, far below the 25 mission tour requirement. The solution seemed obvious: build fighters with longer range. But aircraft range was determined by fuel capacity and fuel consumption rate, both of which seemed fixed by physics and engineering limitations. Fuel capacity was constrained by aircraft size and weight. More fuel meant heavier aircraft, requiring larger engines, consuming more fuel, a vicious cycle that defeated attempts to extend range simply by adding tanks. Fuel consumption rate was supposedly determined by engine design and operating conditions. The Allison V-1710 engine in the P-38 consumed fuel at rates determined by thermodynamic efficiency, air-fuel mixture requirements, and mechanical losses. These rates were established by extensive testing and couldn't be reduced without redesigning the engine, a process requiring years. Or so every aeronautical engineer believed until Charles Taylor proved them wrong. Taylor was a 47-year-old civilian engineer from NACA, the National Advisory Committee for Aeronautics, who had specialized in engine cooling systems. He arrived at Wright Field in March 1943 as part of a civilian technical team investigating various aircraft performance problems. His assignment was to examine P-38 engine cooling issues that were causing overheating during combat operations. The P-38's unique twin-engine, twin-boom design created complex airflow patterns around the engine nacelles. Each engine was housed in a streamlined nacelle, extending forward from the wings, with cooling air entering through intakes in the nacelle nose and exhausting through outlets at the nacelle sides and bottom. This cooling system worked adequately at low altitude but struggled during high-altitude operations where thin air reduced cooling airflow. Pilots reported that engines overheated during extended high-altitude cruise, forcing them to reduce power settings and accept reduced performance. Taylor's investigation of cooling problems led him to examine airflow patterns through the engine nacelles in minute detail. Using smoke generators and high-speed photography during wind tunnel tests, he mapped how air moved through the nacelles under various conditions. What he discovered contradicted everything engineers thought they understood about engine cooling and fuel efficiency. Standard aeronautical theory held that cooling airflow should be as smooth and unobstructed as possible. Any turbulence or restriction in the airflow would reduce cooling effectiveness and increase drag, both undesirable. Engineers designed cooling systems to minimize airflow resistance, creating smooth paths for air to flow from intake to exhaust. But Taylor's smoke tests revealed something unexpected. The smooth airflow that engineers had carefully designed was actually inefficient because air wasn't spending enough time in contact with hot engine components. Air was flowing through the nacelles too quickly, absorbing less heat than it could carry away. The cooling system was moving large volumes of inadequately heated air, rather than smaller volumes of thoroughly heated air. More significantly, Taylor noticed that the engine's fuel-air mixture was being affected by cooling airflow in ways nobody had anticipated. The carburetor, which mixed fuel with incoming air to create the combustible mixture for cylinders, was receiving air that had been cooled by passing through the nacelle intake. This cooler air was denser than ambient air, meaning the carburetor was delivering richer fuel-air mixture than engineers had calculated. Rich mixture, with excess fuel relative to air, produces full power but wastes fuel because not all fuel burns completely. For maximum efficiency at cruise power, engines should run slightly lean mixture where all fuel burns completely. But P-38 engines were running rich at cruise because the cooling airflow was making intake air denser than carburetor calibration assumed. Taylor's insight was that he could simultaneously improve engine cooling and reduce fuel consumption by modifying airflow through the nacelles. Instead of smooth, unobstructed flow, he proposed adding baffles that would create controlled turbulence, slow airflow, and increase air residence time in the nacelle. This would improve heat transfer from engine to air, while also warming intake air before it reached the carburetor, reducing mixture density and leaning the fuel-air ratio. The proposal was aeronautical heresy. Every principle of streamlining and drag reduction said that adding baffles to create turbulence would increase drag, reduce performance, and waste power. NACA engineers, reviewing Taylor's calculations, concluded his theory was flawed and his proposed modifications would degrade performance rather than improve it. But Taylor was confident in his fluid dynamics analysis. He calculated that while the baffles would create localized turbulence, the overall reduction in cooling airflow volume would actually decrease drag because smaller intake openings would be required. The improved fuel efficiency from leaner mixture would more than compensate for any drag increase from turbulence. On April 3, 1943, Taylor received reluctant permission to modify a single P-38 for testing. Working with sheet metal fabricators at Wright Field's experimental shop, he designed and installed baffles inside the engine nacelles. The baffles were simple aluminum sheets positioned to disrupt smooth airflow and create controlled turbulence zones where air would slow down and spend more time in contact with engine components. The modification consisted of 6 baffles per engine nacelle, 2 in the intake section, forcing air to make 90-degree turns before reaching the engine. 2 in the midsection, creating turbulence around the hottest engine components, and 2 in the exhaust section, slowing air before it exited the nacelle. Each baffle was fabricated from 22-gauge aluminum sheet shaped to fit within the existing nacelle structure and secured with standard aircraft rivets. Total material cost per engine, approximately $3. Total installation time per engine, 2 hours. Total weight addition per engine, 4 pounds 8 ounces. The modification was mechanically trivial, which is why NACA engineers were confident it wouldn't work. If something so simple could dramatically improve performance, surely someone would have discovered it during the decades of aircraft engine development. The test flight on April 27, 1943 demonstrated that sometimes simple solutions work precisely because they're simple. Captain Robert Scott, Wright Field test pilot, flew the modified P-38 for 3 hours at cruise power settings, monitoring fuel consumption, engine temperatures, and performance carefully. His initial report documented results that seemed too good to be true. Engine temperatures reduced by average of 18 degrees Fahrenheit at cruise power, completely resolving overheating problems. Fuel consumption reduced by 31% compared to unmodified aircraft at same power settings and altitude. No measurable increase in drag or reduction in performance. If anything, the aircraft seemed to fly slightly better, possibly due to reduced cooling drag from smaller intake requirements. The fuel consumption reduction translated directly into range extension. Standard P-38 with internal fuel and drop tanks, 410 gallons internal plus 300 gallons drop tanks equals 710 gallons total, consumed at 165 gallons per hour, giving 4.3 hours endurance or approximately 520-mile combat radius. Modified P-38 with same fuel capacity but 31% reduced consumption, 710 gallons consumed at 114 gallons per hour, giving 6.2 hours endurance, or approximately 790-mile combat radius. Range increase, 52%. Wright Field engineers, reviewing Scott's data, initially suspected instrument errors or pilot mistakes. They ordered repeat testing with different pilots, different aircraft, and independent fuel measurement systems. Every test confirmed the same impossible results. Taylor's baffles reduced fuel consumption by 30 to 33% and extended range by 50 to 55%. The physics underlying these results were eventually understood through detailed analysis. The baffles created 3 separate effects that combined to improve efficiency. First, increased air residence time in the nacelles, improved heat transfer, allowing engine cooling with lower airflow volume. This meant smaller nacelle intakes could be used, reducing cooling drag by approximately 8%. Second, warming intake air before it reached the carburetor, reduced air density by approximately 12%. This leaned the fuel-air mixture from rich stoichiometric ratio of approximately 14:1 to optimal lean cruise ratio of approximately 16:1. At lean cruise mixture, all fuel burned completely, eliminating the waste inherent in rich mixture operation. Third, the controlled turbulence actually improved airflow distribution across the engine, ensuring all cylinders received adequate cooling rather than having some cylinders run hot while others ran cool. This allowed overall cooling airflow to be reduced while maintaining adequate cooling for the hottest cylinders. If you're fascinated by these stories of World War II innovation where questioning established wisdom created breakthrough capabilities, please subscribe to our channel and hit that notification bell. We share these incredible untold stories of engineering creativity that changed history. The implications were staggering. If similar modifications could be applied to other aircraft, the entire American fighter force could gain 50% range extension essentially for free. The P-47 Thunderbolt, P-51 Mustang, and other fighters could potentially reach targets deep in Germany that were currently beyond escort range. But institutional resistance to Taylor's discovery was intense. Lockheed engineers, who had designed the P-38 cooling system, were insulted by the implication that a NACA engineer working at Wright Field had found fundamental flaws in their design. They argued that Taylor's results were anomalous, that the modifications would fail under combat conditions, and that production aircraft couldn't be modified without extensive engineering analysis and testing. Republic Aviation, manufacturer of the P-47, was equally resistant. Their engineers insisted that the P-47's radial engine cooling system was completely different from the P-38's inline engine design, and that Taylor's baffles wouldn't provide similar Benefits. They discouraged Wright Field from even testing modifications on P-47 aircraft. North American Aviation, manufacturer of the P-51 Mustang, was more open to testing but skeptical that significant improvements were possible. The Mustang already had excellent range compared to other fighters, and North American engineers doubted that simple baffles could improve on their carefully optimized design. The bureaucratic battle over Taylor's discovery mirrored previous conflicts over unauthorized innovations. Official approval processes required committee reviews, engineering analyses, and formal testing protocols that would take months to complete. Meanwhile, bomber crews were dying on every deep penetration mission for lack of adequate fighter escort. Major General William Kepner, commanding 8th Air Force Fighter Command, broke the deadlock with a command decision similar to those made by Bradley for Clark's night vision modifications and Doolittle for Harrison's fuel system modifications. On June 8, 1943, Kepner ordered immediate field modification of 50 P-38 aircraft using Taylor's baffle design. The modifications would be installed by depot maintenance personnel, and the aircraft would enter combat operations immediately. Kepner's order stated, "Recent testing demonstrates that nacelle airflow modifications can extend P-38 range by over 50% with no performance degradation. This capability is operationally essential for escort missions to Germany. 50 aircraft will be modified immediately for operational evaluation. If combat results validate testing data, all P-38 aircraft will be modified as rapidly as depot capacity permits." The operational evaluation began in July 1943, when the 55th Fighter Group received 32 modified P-38s. The group's first long-range escort mission, to Kassel on July 28, demonstrated the modification's effectiveness. Modified P-38s escorted bombers to target and returned to England with fuel reserves that would have been impossible for unmodified aircraft. Colonel Jack Jenkins, commanding 55th Fighter Group, reported, "Modified aircraft performed exceptionally well during extended range mission. No overheating issues despite prolonged high-altitude operation. Fuel consumption matched test predictions, allowing us to escort bombers to targets we previously couldn't reach. This modification should be implemented fleet-wide immediately." German fighter pilots, accustomed to American escorts turning back at predictable points where fuel limitations forced their return, were shocked when American fighters suddenly appeared over targets deep in Germany. Hauptmann Johannes Steinhoff, commanding Jagdgeschwader 7, wrote in his tactical diary, "American escort fighters are now appearing over targets we believed were beyond their range. Either they have deployed new aircraft with extended range, or they have modified existing aircraft. Either way, our assumption that distance provided protection has been invalidated." The success of Taylor's modifications on the P-38 finally convinced manufacturers to test similar approaches on other aircraft. Republic Aviation conducted tests on the P-47 in August 1943, discovering that, despite their initial skepticism, nacelle modifications provided similar benefits. Fuel consumption decreased by approximately 28%, extending the P-47's already impressive range by over 40%. North American Aviation tested modifications on the P-51 in September 1943. The Mustang's already efficient cooling system showed smaller improvements than the P-38 or P-47, but still achieved approximately 18% fuel consumption reduction and 25% range extension. By October 1943, all three primary American fighter types were being modified with Taylor-designed cooling system baffles. The modification program, initially resisted by manufacturers and NACA engineers, became the highest priority engineering change for fighter aircraft. The strategic impact was immediate and decisive. Fighter groups equipped with modified aircraft could escort bombers all the way to targets in central Germany and return safely. The combination of extended range and effective escort dramatically reduced bomber losses on deep penetration raids. Loss rates dropped from over 20% on unescorted missions to under 5% on missions with adequate escort. The operational data was unambiguous. 8th Air Force bomber losses, August through October 1943, unescorted missions, average 22.4% loss rate per mission. Missions escorted by modified long-range fighters, average 4.7% loss rate. The difference represented thousands of bomber crew members who survived because fighters could stay with them throughout missions. German Luftwaffe fighters, facing American escorts at ranges they'd never encountered before, found their tactical situation transformed. Previously, German fighters could position themselves beyond escort range and attack bombers without fighter interference. Now, American fighters were present throughout missions, forcing German fighters into disadvantageous engagements. Major Gunther Rall, one of Germany's highest-scoring aces, described the impact in post-war interviews. When American fighters began appearing over targets like Berlin and Leipzig, we knew we'd lost air superiority. We could no longer position our fighters optimally because American escorts were always present. Our losses increased dramatically, while our effectiveness against bombers decreased. The extended range of American fighters was more decisive than any other factor in the air war over Germany. The technical specifications of Taylor's modifications were eventually standardized across all American fighter aircraft. For inline engine aircraft like the P-38 and P-51, 6 baffles per engine nacelle positioned to create controlled turbulence and increase air residence time. Baffle dimensions and positions optimized for specific nacelle geometries through wind tunnel testing. Material: 22-gauge aluminum sheet formed to match nacelle contours. Installation: 4 hours per engine by qualified maintenance personnel. For radial engine aircraft like the P-47, 8 baffles around engine cowling positioned to improve airflow distribution and reduce cooling air requirements. Different baffle geometry required due to radial engines' different cooling requirements. Material and installation time similar to inline engine modifications. The performance improvements across the American fighter fleet were documented in comparative testing. P-38, Lightning, fuel consumption reduction 31%, range extension 52%, combat radius increased from 520 miles to 790 miles. P-47 Thunderbolt, fuel consumption reduction 28%, range extension 43%, combat radius increased from 475 miles to 680 miles. P-51 Mustang, fuel consumption reduction 18%, range extension 25%, combat radius increased from 650 miles to 812 miles. These range improvements transformed strategic bombing operations. Targets that had been beyond effective escort range became accessible. The entire German aircraft industry, concentrated in central and southern Germany, suddenly faced coordinated bomber and fighter attacks. German oil production facilities, critical to continued military operations, came under sustained attack that German fighters couldn't effectively counter. The Big Week Offensive, February 20 through 25, 1944, demonstrated the transformed strategic situation. American bombers, escorted by long-range fighters throughout their missions, attacked German aircraft production facilities across Germany. Despite fierce German fighter resistance, bomber loss rates remained under 7% due to continuous fighter escort. German fighter losses exceeded 200 aircraft, with over 100 pilots killed, losses the Luftwaffe couldn't replace. Albert Speer, Germany's armaments minister, wrote in his memoir about the impact of American air superiority enabled by long-range escort. The appearance of long-range American fighters over our industrial centers marked the true beginning of our defeat in the air. We could no longer concentrate our fighters where they were most needed because American escorts were everywhere. Our aircraft production, which we had successfully dispersed to avoid bombing, couldn't be protected from fighter attack. The extended range of American fighters was perhaps the decisive factor in our losing the air war. Taylor's modifications continued evolving throughout the war as engineers refined understanding of airflow dynamics and thermal management. By early 1945, fourth-generation baffles incorporating lessons from hundreds of thousands of flight hours had reduced fuel consumption by up to 38% on some aircraft, extending range by over 60%. The broader implications of Taylor's discovery extended beyond immediate military applications into fundamental aeronautical engineering principles. His work demonstrated that established understanding of engine cooling and fuel efficiency was incomplete, that decades of wind tunnel testing and theoretical analysis had missed critical interactions between cooling airflow and engine performance. Post-war analysis by NACA engineers acknowledged the oversight that had prevented earlier discovery of cooling system inefficiencies. A 1946 technical report stated, pre-war cooling system design emphasized minimizing cooling drag through smooth, unobstructed airflow. This approach optimized one parameter, drag, while inadvertently degrading other parameters, including heat transfer efficiency and fuel-air mixture calibration. Mr. Taylor's insight was recognizing that overall system performance could be improved by accepting localized turbulence to optimize heat transfer and mixture control. This represents fundamental advance in understanding engine-airframe integration. If you've enjoyed discovering how one engineer's questioning of established aeronautical wisdom transformed air combat and helped win World War II, please subscribe and hit the notification bell. We share these remarkable untold stories of innovation and determination. Your support helps us continue bringing these stories to light. Modern aircraft design incorporates principles derived from Taylor's work. Current fighter aircraft use sophisticated computational fluid dynamics to optimize cooling airflow, but the fundamental insight that controlled turbulence can improve overall system performance remains central to design philosophy. The principle that localized inefficiency can produce global efficiency appears throughout modern aerospace engineering. Charles Taylor's wartime service ended in September 1945. He returned to NACA, where he continued research on aircraft cooling systems and engine airframe integration until retirement in 1958. He received the NACA Distinguished Service Medal in 1946 for his contributions to fighter aircraft range extension. The citation credited him with developing modifications that extended range by 50% and significantly improved strategic bombing effectiveness. Taylor rarely discussed his wartime work publicly. In a 1965 interview with NASA's History Office, he made brief comments about the baffle modifications. The discovery wasn't particularly sophisticated. I simply questioned whether accepted design practices were actually optimal and found that they weren't. The resistance I encountered from established engineers taught me that questioning conventional wisdom requires not just technical analysis, but courage to challenge institutional beliefs. This modest assessment understated Taylor's achievement. While the technical modifications were indeed mechanically simple, recognizing that established aeronautical theory was incomplete required insight that eluded thousands of engineers who had worked on aircraft cooling systems for decades. Taylor succeeded because he approached the problem without preconceptions about what should work and focused instead on understanding what actually did work. The thousands of American fighter pilots who flew extended-range missions, escorting bombers to Germany, rarely knew their aircraft had been modified to extend range. They simply knew they had enough fuel to complete missions, which seemed unremarkable until one understood the physics that made it possible. Lieutenant Colonel James Goodson, P-51 pilot with 4th Fighter Group, who flew 100 combat missions, including numerous deep penetration escorts to Berlin, wrote in his memoir, "We flew missions to Berlin and beyond, sometimes spending 4 or 5 hours airborne, and always had adequate fuel reserves. I never thought about how this was possible until after the war, when I learned our aircraft had been modified with cooling system baffles that reduced fuel consumption by nearly 20%. That modification probably saved my life on several occasions when fuel was critically low after combat." The strategic bombing campaign against Germany, which historians credit as critical to Allied victory, was enabled by technologies both famous and obscure. The Norden bombsight improved accuracy. Radar allowed all-weather operations. Proximity fuses improved defensive firepower. But none of these mattered without fighter escort. And fighter escort was impossible without the range extension that Taylor's cooling system modifications provided. The modification that cost $6 per engine and required 4 hours to install provided range improvements that would have cost billions and required years to achieve through new aircraft development. It represented aerospace engineering at its most elegant. Profound capability improvement through simple modification based on deep understanding of physical principles. The story of Charles Taylor's cooling system modifications demonstrates that breakthrough innovations often come from questioning assumptions rather than accepting conventional wisdom. Every aeronautical engineer knew that smooth airflow minimized drag. Taylor questioned whether minimizing drag actually optimized overall performance and discovered it didn't. Every engineer knew that established cooling system designs represented decades of refinement. Taylor questioned whether those designs were actually optimal and found they weren't. His willingness to challenge institutional knowledge, to test theories against reality rather than accepting theoretical predictions, created capability improvements that experts had declared impossible. When NACA engineers calculated that his baffles would increase drag and degrade performance, Taylor built prototypes and proved the calculations were based on incomplete understanding of system interactions. The fighter aircraft that flew extended-range missions throughout 1944 and 45, protecting bomber formations that destroyed German war production, carried Taylor's modifications in their engine nacelles. The baffles that created controlled turbulence, slowed cooling airflow, and optimized fuel-air mixture were invisible to pilots and ground crews who benefited from their effects. But those simple aluminum sheets, positioned to disrupt smooth airflow in ways that violated established aeronautical principles, changed the air war over Europe. They transformed American fighters from short-range interceptors into long-range escorts. They made strategic bombing sustainable by reducing bomber losses from 20+% to under 5%. They helped establish air superiority that enabled invasion and victory. Today, the principles Taylor discovered through questioning conventional wisdom are taught in every aerospace engineering program. Students learn that overall system optimization sometimes requires accepting localized inefficiencies, that established design practices should be questioned and validated rather than accepted uncritically, and that simple modifications based on deep physical understanding can produce capabilities that complex solutions cannot achieve. The crazy airflow trick that made planes fly 50% farther wasn't crazy at all. It was brilliant insight disguised as simple modification, proof that sometimes the best innovations come from having the courage to question what everyone knows and the wisdom to discover what actually works. Charles Taylor's cooling system baffles demonstrate that breakthrough capabilities can emerge from $6 modifications when those modifications are based on understanding that transcends conventional wisdom. American fighters started flying 50% farther, not because of new engines or larger fuel tanks, but because one engineer questioned whether established cooling system designs were actually optimal. He discovered they weren't, designed simple modifications that everyone said wouldn't work, and proved that sometimes the craziest ideas are crazy only because nobody else thought to question what everyone assumed was true. In doing so, he changed air combat, enabled strategic bombing, and helped win the war through aeronautical insight that cost less than a tank of fuel but proved more valuable than squadrons of aircraft.